quick explainer on the origins of centripetal forces for a car on a bank. Here's my sleek looking car, I think it's a BMW, on a bank. When we're talking about a bank, we mean raised at an angle theta. Now instead of going up and down, we're imagining we're describing a bit of circular motion around this kind of steeped thing. So if you can see the back of my car, it's moving away from me and we're imagining it's going to follow circular motion. So in this case, if we're following circular motion, the center of the circle is somewhere over here. In other words, we're going to have to resolve our forces so that we find the horizontal force, and that's going to be my centripetal force. The question is, what provides the centripetal force here? Well, we've got two main forces that we need to consider. We're going to ignore friction here. Okay, first one, we've got W, okay, the weight of the car, and then we've got the normal force. The normal force is at an angle which is 90 degrees to the surface itself. That's going to be important because we're going to resolve forces and we're going to see how those balance one another. Now obviously, if we're rotated by an angle theta here, my whole system has been rotated anti-clockwise by theta, and so therefore I'm expecting a theta in here somewhere. Okay, we've got a theta in there. I've taken the car away just to make our life a little bit easier. You notice now my n clearly has a vertical component and a horizontal one. Okay, well, if we are not going up or down the slope, or up or down in the y direction, okay, then we've got a component n cos theta of my normal, and n sine theta, which is the horizontal component. Vertically, we must have mg equal to n times cos theta. In other words, the vertical component of the normal force must balance with the weight. Okay, so these guys, the vertical components there, are not providing centripetal force because they're balancing each other. In other words, the total of those forces is zero. We're not rising up or down. However, my green force here, which is my centripetal force, must be provided by the horizontal component of my normal force there. In other words, we've got mv squared over r is equal to n times sine of theta. Okay, we can take a few limiting cases. One, we could think about when theta is equal to 0. In other words, when we're on a flat bank. Okay, well in that case, we would have cos of theta, cos of 0 is 1. In that case, the normal force would be equal to the weight, and that's what we experience when we've got non-accelerated motion horizontally. Also, mv squared would be equal to n sine theta. In that case, sine of theta would be 0. We wouldn't be doing circular motion. We'd simply be following a straight line. The other limiting case, theta equal to 90. Well, if theta is equal to 90, cos of 90 is 0. Our cos of 90 would give us 0. We would have no normal force in that sense. Okay. However, our normal force going horizontally, n would be n times sine of theta, which sine of 90 is 1, and therefore we'd be looking at pure horizontal motion. Okay, don't worry too much about those limiting cases. Focus more on simply the equalizing of the vertical and horizontal forces. In this case, I'll repeat, vertical force is are balanced, mg equal to n times cos theta, and in the case of the horizontal force, the horizontal component of the normal is providing the centripetal force.